All right, 1, 2, mic check. All right, good afternoon, ladies and gentlemen. Good evening. Welcome to this series of tutorials with me, Aubrey. And even as we start, I am requesting that you like, you subscribe, and ring the notification bell because my stats right now are showing that only a 50% of you have subscribed to the channel. So to support the channel, please subscribe and share to other people so that they gain the same knowledge that you are going to gain. So now in today's lesson, we are starting Cauchy, or let me say complex integration. All right, we are starting complex integration, and in complex integration, we'll be looking at two, I would say, two theories in integration that we will be working out with. The first part, I think we studied line integrals, and now the second part of complex integration deals with Cauchy integration. All right, where we'll be using the Cauchy theorem to do integration. Now, this is very simple. You'll be able to catch on. So now, let me just prove the Cauchy's theorem. This is the theorem among others that we'll be using to make integration. All right, and the theorem states if f of z is analytic, right, in this region or in this contour, it's a circle. All right, if it's analytic in that, meaning that the CRI equations hold in this region, then the integral of f of z dz is equals to 0. All right, so what this theorem is saying is that usually you'll be given a region where you will be integrating from. All right, you'll be given a region where you'll be integrating on, and if you find that this function is analytic in that region, all right, in that region, then its integral is equal to 0. In other ways, if this function has no any singularities or pores in this region, then its integral is equal to 0. Now let's do the proof of the theorem. All right, so proof. All right, so we know that z can be written as x plus iy because it's a complex number, and we know that f of z can be written as u plus iv. All right, so we have f of z can be written as u plus iv, and this z can be written as x plus iy. So now, if we were to rewrite this, we would say uh, the integral of f of z dz would be equals to u plus iv, which is this part, f of z, times, so now there's z here, so we can distribute, z is x plus iy, so we can distribute the d inside, so it will be dx plus I dy. All right, so plus I dy, so we just distributed this and we get that. Okay, so now from here we will multiply this and that and so on, just the way we multiply this and this and that, this and this and this and that. And when we multiply, we group the real parts and the imaginary parts. All right, so multiplying and grouping the real parts, we're going to have that. Okay, we're going to have that. Okay, so now we've multiplied and grouped the real parts. Remember, we are showing that the integral, if a function is analytic in a given curve, its integral is equals to 0. If a function is analytic in a given curve, or if it has no singularities, then its integral is equals to 0. So this is how far we've come. So now from here, we can use Green's theorem here. Okay, we can use Green's theorem on this part and on this part. What does Green's theorem state? All right, so Green's theorem states that if you have m dx plus n dy, this is equals to the double integral of n, the double integral of n the double integral of n dx, okay, then minus the integral of m dy. So minus m dy, okay. So the first one becomes the second one. The second one becomes the first one. And you see here we have dx. The dx part becomes on the denominator there. The m goes that side. The n comes here and the dy goes there. So this is Green's theorem. Then you have dx dy. So you need to memorize Green's theorem. All right, so now applying Green's theorem here. So you see that we have dx. Are you seeing that? So you should make sure that we have dx, then dy. So meaning that in this case, this is our m, and in this case, our n is negative. Our n is negative. All right. So our n is negative. So if we were to put it here, then it would have been negative the n, okay? So now applying Green's theorem, we're going to say integral of that. So as we said, this will be negative because our n is negative vi. Our n is negative v, and since n is negative, we're going to say negative the v dx. The v dx. So plus, so now this is minus, always there is a minus. So since our n is positive, so it just be minus du dy, then the x dy. Okay, same applies here. Our v, okay, our u is our n, so it will be du dx. So since it's positive, it just be plus du dx minus, always it's minus, right? So but if v is positive, so if it was negative, this would have changed to plus, okay? If v was negative, this would have changed to plus, so it will be just the v like that, the x dy. So we've applied Green's theorem to this, and we get this right here. Now remember we said f of z is analytic, all right? So since f of z is analytic, then the CRI equations should hold. And the CRI equations states that the u dx is equals to the v dy, and negative the v dx is equals to the u dy. All right? So meaning in the equation, or in our previous equation, wherever there is the u dx, we can replace with this, okay? Wherever there is the u dx, we can replace with that, and where there is negative the v dx, we can replace that, or we can choose to replace where there is the u dy, we replace negative the v dx, then this will be plus, and where there is this, we replace that. So whichever way you choose, you will see that this now will become what is the v negative the v dx is equals to the u dy. Then here we have minus du dy, then the x dy, okay? Then the other part as well, du dx is equals to the v dy minus the v dy. And as you can see here, as you can see right here, this minus this will give us 0, and this minus this will give us 0. That is to say that this is equal to 0 plus 0, which is just 0. All right, so this proves our Cauchy's theorem. All right, this is Cauchy's theorem. All right, so you can copy it down. All right, so this is Cauchy's theorem, and From here, we are going to look at some examples of where we can apply Cauchy's theorem. And yeah, so stay tuned. Remember to subscribe to the channel. Remember to subscribe to the channel and leave a like and all those good stuff. See you in part 2.